All right, welcome to today's Rubin Science Assembly. Today it's going to be a couple of hands-on tutorials on source detection and force photometry. But as always, let's start with some announcements before we head into our tutorial. And questions are welcome at any time. I can see your hands raised, I can see the chat, so just go ahead and try to interrupt me. If I don't notice your hand or your chat message, just unmute and ask the question as we go. We have a few announcements. We have a couple of, in case you missed it, announcements. RubinObservatory.org has all the Rubin First Look images from a couple weeks ago. Data Preview 1 was released on Monday, June 30th. You can find all the information at dp1.lsst.io. The Rubin Data Academy happened the week of Monday, June 30th. You can find all the recordings and all the slides on the Data Academy website. You can find all upcoming events in rubinobservatory.org, the Force Scientists website. The Rubin Science Assembly is upcoming. This is actually the last one. We're going to be on a break from now until probably about mid-September. So you'll see announcements go out when we do resume our science assemblies in the fall. And the big announcement, of course, next week is the Rubin Community Workshop 2025. We're back in Tucson. It is fully hybrid. Virtual registration is still open. So if you were thinking about attending some of those sessions, do register virtually. It is free. It's just we need to make sure your account works so that you have access to all the Zoom links and the Slack space and stuff. So get registered for that if you're interested. If somehow this is your first Rubin event, or you're completely new, you want to start out by getting a Rubin Science Platform account. Just going to link you straight to these slides for these handy links. So links to learn more about the first data release, a link to the For Scientists webpage with general information that I just mentioned, and the place to go for questions and to get help is community.lsst.org. So if you're new here, welcome. These are the handy links to get you started. As always, I like to remind people that you are users of the Rubin Science Platform, the data products, all our services and tools, and you have a committee whose job it is to advocate for you on your behalf. So if you are having issues, if you're concerned that the data products and services aren't sufficient for you to do the science that you want to do with Rubin, Users Committee is the place to go. They love getting feedback from people. Every 6 months, they make reports directly to our director with findings and recommendations for improvements. So that's great. Their next meeting is part of the Rubin Community Workshop. It's Thursday morning, and we would love to have you attend virtually if you're available. Every Thursday, right after this Rubin Science Science Assembly, the Link Frameworks folks also host a drop-in that helps people to use all of the wonderful software that they are developing for science with the Rubin data. So consider following some of these links and finding out what they're working on and asking them for help if you want to use their stuff. That ends the announcement portion, and we can head into, oh, it is someone's first Rubin event. It's wonderful. Okay, you should have all the links there. I'm going to put specifically rsp.lsst.io. That's where you go and you'll find sign up for account right here. So if you're new, this is the place you want to go to first to get an account in the Rubin Science platform. You won't be able to follow along hands-on with the tutorials that I'm about to show you, but once you've gone through the process to get your account set up, you would be able to. So that's where you should start today. Any other questions about any of the announcements or resources before I head into our tutorial? Wonderful. Nice to have you. Okay, no one else is shouting for anything related to the announcements. So let's get started. Let's do our tutorials. So the first thing I want to mention is that today's tutorials So as always, all of the tutorials, like executed rendered versions of all of our notebooks, are available in the DP1 documentation. That's at dp1.lsst.io. Our notebooks, they have 3 levels. The 100 level is all how-to RSP functionality. Level 200 is all about the data products. There's a separate tutorial for every image type, every catalog type. And then at the 300 level, it's all science demonstrations. So usually end-to-end scientific analysis demos. Today's tutorials are at the 100 level. So we're learning how to use some of the RSP functionality. And today in particular, we are all the way down. So these are different series at the 100 level. How to use Jupyter Lab, how to access catalogs, how to access images and display them, how to use the Butler. Today we're all the way down in our 105 series on image reprocessing. So these are going to be a little more advanced. We're going to use the Butler, but this is not a tutorial on how to use the Butler. Those are all in the 104. We're going to use images, but these are not tutorials about image access and display. They're more about reprocessing, how to do source detection, how to do force photometry. So that's where we are in context. So if you're new, these might seem a little bit high level, and they are some of our more advanced how-to tutorials at the time. I want to point out that in our 105 series, there's a 105.1, how to use the LSST science pipelines, which has sort of very general information about like, what is a pipeline? What is a task? A task is like one command, one module of a pipeline. It's got some tips on how to learn about the tasks and modules, some of which we will be using today. How to sort of explore what's in the science pipelines, how to figure out what tasks you might use for different things. We're not going to go through this tutorial step by step, but it is here as kind of like a basic reference. And so I wanted to just make you aware that in this series of 105, there is a first one that's like kind of a basic how-to. And then 105.2 is what we are going to run through today, detect and measure sources. And then 105.3 on force photometry. So we're running through the second and third one in this 105 series on image reprocessing. And the full rendered versions are always available in the documentation if you need them, but we're going to do it for real. We're going to run through them today together. So we start at data.lsst.cloud. And if you've been here before, you've probably already gone and logged in. We're going to enter the notebook aspect. I'll log myself in. Since I'm touching data today, I'm going to use a large container. The small is really for only if you're like accessing notes files, or basically if you're doing something that doesn't involve actual access of data, you can pick small. Otherwise, always go with large. So I'm going to start up a large container. All right, my container has started up, and this is always the landing page that you will always come to first. It's a welcome page with a bunch of handy links, like back to the DP1 documentation that I was just showing you. Since this landing page, this welcome.md file always shows up, you always start out in your /notebooks/tutorials folder as well in the file browser at left. So that's like the default that you will always find when you enter. Going to close that, and I'm going to go back to my home directory because I generally like to start there. So most of you should have been able to get to about this point. If you're having login issues, we can't deal with them right now, but do post in the chat if you're having login issues, or even better, in the community forum at community.lsst.org so that we can help you with those login issues later. You post in the support channel here. Just make a new topic, tell us about your issue, and we'll get it fixed later. All right, back in the Rubin Science platform, let's open up the tutorial that we want for today. So we're using data preview 1. We're in the 100 level, learning how to, series 105 on image reprocessing, 105.2, detect and measure sources. We're going to open that one. And it will open. If this is one that you've already opened before, you'll get a little, if you opened it and you modified it and then you saved it to disk, when you try to get another one from the drop-down menu, it will say, hey, do you want to overwrite the version that you already have? We recommend to always overwrite. You always want to be getting the freshest tutorial that you have, unless you have downloaded one of the tutorials and then done a bunch of work in it, then you wouldn't want to overwrite it. So you may or may not have got a pop-up about overwriting. I didn't have a copy of this yet. And they do get saved automatically in notebooks, tutorials, DP1, 105. It got saved automatically here in the file structure, and you can tell it's the one that's open because it's got the little green dot next to it. All right. Okay, our file is open and we're ready to go. So in this particular tutorial, we're going to be using 3 tasks from the LSST science pipelines to do source detection, deblending, and measurement. They're called source detection task, source to blend task, and single frame measurement task. Very reasonable. All of this we're doing today, and the single frame measurement task name is a clue. We are doing measurements on single image. So we're doing them on visit images, not the deep stacked co-added images. So these are all for how to do source detection and deblending on a single visit image. That serves as our introduction. Let's move on and import the packages that we need. We have like a bunch of display packages. So the butler obviously gives us access to the images. Got some display packages, and then those 3 tasks that I mentioned are all coming from the LSST measure package. So let's go ahead and import all of those. Wonderful. And as you do this, if you get an error or anything weird happens that doesn't happen in mine, you just shout and let us know, and we'll figure it out together. So once we've imported the packages, we want to define some parameters and functions. First one, we want to instantiate the butler so that we have access to the data. We're going to be grabbing an image that's from a central region of the extended Chandra Deep Field South, and the central coordinates of that field in RANDEC. We'll just define them now to use them throughout. And then we want to set the visual backend. So we're going to end up displaying a visit image, and then we'll end up plotting markers at the locations of the sources we detect in that image, and we're going to use Firefly for that. Firefly is our internal sort of like in-house built interactive image viewer. So we're going to open that up. It's opened in a separate tab. So we'll just have that open and ready for when we want to display an image. All right, we're set up. We've imported our packages. We're ready to go. Now we need to get a visit image in order to do source detection on. So we set up our query here where we're going to be using, get an R-band visit image that contains the right ascension and declination that we defined before. So first we're just setting up our query and setting up the parameters that will define that query. That's great. And now we want to actually perform the query for data sets on the butler. So we're going to pass the query and those parameters that go with the query to butler query data sets. We want a visit image out of it, and we want our results ordered by timespan.begin, so that's the starting time of the given image. So we're getting all the visit images in the R band that overlap our RANDEC, and they're going to be sorted by the acquisition time. And we're just going to get the first one from that list, right? That makes sense. Instead of having to know what time the first one is, we're just going to grab the first one off that sorted list. We assert that only one was returned. We print the data ID to see when it was. And there we go. So it's giving you the visit number, the day of the observation for that particular visit. And we've got the reference out of the list of dataset references for that first visit image. And the next step after doing that Butler query and getting the reference for the visit image that we want is to actually get the pixel data for that visit image using the butler.get statement and passing it the data ID that we had defined from the ref. There's various ways to use butler.get. We actually didn't need to do this here. You could replace this, I think, just with ref and it would work the same. But how to use the butler is a topic for a different day. So we're doing it this way today. So we've got the visit image, returned it. So now the pixels for that visit image are now in memory. As is taught in other tutorials, visit images come with 3 planes. They come with the pixel data plane, they come with the mask plane, and a variance plane. Since we're going to be redoing source detection in this particular notebook, we want to remove and clear the mask plane for which pixels are detected, so that we're saying, let's go back to before our source detection was done on this visit image, clear the mask plane for detected pixels so that we can redo it. So we clear that mask plane. Excellent. Okay. The next step is to set the source table schema. So when we run the tasks to do source detection, they do need to be told a little bit about what they're about to detect and measure. They need sort of like a container to put the results in, and that is setting up the schema first. So the first cell just creates a very standard minimal schema. One of the nice things about the science pipeline, you don't have to know what that looks like. You can just say, make me this standard minimal schema that the science pipelines needs in order to run the task. That's it. That's all we're saying here. So you don't have to set it up. There is a weird little bug where 2 of the columns that it expect aren't made by default, so we have to make them. If we didn't do it here, you would find out they were needed because later on you would get an error message saying, hey, your schema didn't have these columns. And you'd be like, okay, so I'll go back and make them. That's how we figure this out. This should be fixed in the future, but for now, we add these 2 fields to hold the RA, the right ascension and declination errors. Just add them in there because we know it's going to need it. And create a container to hold just some metadata about the tasks as they run. All right, so we've gone through, we've selected the visit image, we've set up our source table schema. Now it's time to configure the tasks. So those 3 tasks that I mentioned before, they each take a configuration. This sets the parameters that the task uses to run. You can, throughout this notebook and others, like especially 105.1, sort of the beginner how-to there, has sort of some optional things for how to get help statements and doc strings. Usually they're very long, but they are there to inquire more about what this configuration class thing is that you've got and that we're using. So there's one way to learn more about it, but just sort of looking at what the tutorial is doing is often sort of the more informative thing. So the first step here is to define config as like this temporary thing to hold the source detection task. Config class, it knows what the different parameters are available to configure for the source detection task. One of them is the threshold value. The default detection threshold value that's used throughout Rubin Observatory Science pipelines is always a 5 sigma. A signal to noise ratio greater than 5 always means detected pretty much in any source detection task that's run and for any table that's created. So because we want to do something a little different here, when we're rerunning source detection, we're going to set that threshold value to 4 instead of to 5. So we're going to end up detecting fainter things in our visit image than were in the corresponding source table for this visit image, because we have a lower threshold value. The threshold type, we're going to keep it at standard deviation, so that this 4 that we've defined corresponds to 4 sigma. So we set up those configuration parameters, and then it gets passed and defined and used to define source detection task. And this was always temporary, so we just delete it. You just create this little config, pass it as you define source detection task, and you move on. So that is defining configuration parameters for source detection task. And then you can do it. We're not going to change any config parameters for source to blend task. So we just instantiate source to blend task without passing any special config parameters, leave them at their default. Deblending is very complex. This tutorial is not teaching anything about deblending. That's all for another time. It's just going to do the standard default level of source deblending as is done in the science pipelines. And then finally, for single frame measurement tasks, also no special configuration is needed for this tutorial. So we're just showing that a config is instantiated, it's all the defaults, it is also passed. Source measurement task also needs to be given that algorithm metadata container when it runs. So we set that up. So now we've instantiated the 3 tasks that we're going to be using: detection, deblend, and measurement. The last thing to do before moving on is creating a source table that will hold the output. So just set that up and this is like so we're passing it the schema, and it is making the default thing that is a source table that it knows that it needs to make. You don't have to know a lot about the structure. It's making the right thing for the job. Here in section 2.3, it's just sort of showing you some optional things. So for example, above we set the threshold value to 4. Maybe later when you're playing with this, you want to reset it to 10 so that you're only detecting very high signal to noise ratio objects. A couple more options for investigating more about source detection task and more about its functions. These are all optional ways to sort of investigate the things that you're using. We won't investigate those right now. We will just get rid of this schema thing that we no longer need because we only needed it to instantiate the tasks, and now we can let it go. So with our tasks instantiated, we are now ready to actually run source detection. Just going to pause for a second. I don't see any hands or any questions in the chat, but just pause also in case you're a little bit behind from where we had to execute it up to. Yeah, go ahead, Catherine.
I had a question a little while back, actually. If you go back to the part of the notebook where you were querying the data, is there a resource somewhere in a tutorial or online or somewhere that has the valid like schema, I guess, for setting up a query, like this band.name and visit detector underscore region dot region? Yeah, where we could find what are sort of the valid ways to query a data set.
Absolutely. That is all Butler related. And so I think if you work through 104.1, get started with the Butler, that's like super short and simple. And then 104.2, explore the Butler repo, and 104.3, image queries with the Butler. Especially 104.2 goes through like, what are all the data set types? What are all the things that you can ask for? what are all the dimension and elements? What are all the various things that you can query on? How to query on tracked versus band? How to know how to connect for a given data set type? What are the different things that you can compose a query out of? So this kind of, it takes you through all of that kind of stuff. What are the schema? How to find the schema? How to find that? Does this one, this isn't for visit, it's for deep coad. But if you did this for visit image, this is how you would discover that you can query on like visit underscore region dot region. And so, yeah, there, so you can do the same sort of printout for visit image and discover that kind of thing. It should takes you through dimension records. So like, what are all the bands? What are all the options for if I can query something by band, what types of bands are there that I could constrain on? So I think this is what you're looking for, 104.2.
Thank you.
Yeah, you're welcome. Any other questions before we go on? Alrighty, let's do it. Let's run source detection. So now we have the task has been all set up. It's got its schema, it has its configurations. We just do a dot run, say put all my outputs in the table, and we're running on this visit image that we got from the butler. All right, it's running, it's on its way. That's great. It gives you a little bit of messaging about how well that it did. And we can print the number of positive peaks that it detected in the image, which is about 4,000. And we can also then extract from this big like results container, we can extract just the sources and define sources just to hold that source table. Here you'll see that the sources that it found is just over 3,000. And that difference is that number of positive peaks is like every positive peak, even if it's sub-threshold. But we said a source is only detected if it has a signal to noise ratio greater than 4. And so that's the difference between positive peaks is everything, sources are the things that met our detection threshold. Let's do this option to quickly display what this thing is called sources. It's just a table. Right now, all we've done is detect. So basically it's just like got the XY values for all of the sources that were detected, and pretty much everything else, nothing's really been measured yet. So most of this table is still filled with nans because it's literally just a list of the sources locations that were found. To keep going, we need to do source to blending and source measurement. So first we run source to blend task and let the deblender do its thing. And it tells us that's great. There were over 3,000 sources. I found that 391 of them were actually combined and could be separated out into children sources. The total number of children that they found was over 1,000. So you can see right away that if 391 sources were deblended and created, over 1,000 children, there's like 2 or 3 or more children per source. And so now with deblending, we've increased it to over 4,000 individual sources that it was found. Once the deblending is done, the source measurement task can be run. And that's what's going to get you fluxes, shapes, sizes, all of the measurements of the actual sources. So now it's doing that. It's making measurements on all the sources and all the deblended child sources. All right, that executed fine for me. Hopefully yours is running fine as well. The next cell is something I've never fully understood why it's necessary, but apparently for now it is necessary to make a copy to continue on to use this new source table in the rest of the notebook. Let's give it a quick display as an AstroPi table so that it'll be nicely formatted. And now you can see RA and Dec get measured in radians, and you can scroll over and you can see that some of the centroids and pixels, those columns have been populated. There are a lot of columns. There's a lot of flag columns, as you can see everything here that's just like a true or false is a flag column. Oh my gosh, somewhere in here there's actual measurements, and we'll get back to numbers. Yeah, so we have some blendedness parameters, some instrumental flux parameters that are in counts. All of that is all in here. And you can kind of tell the reason why we keep this cell commented out is because the tables are they're very large. They're very, very wide tables that do a lot of measurements for you. There is also the option to write your source table out to file, should you so desire, or the FITS file. This is not really recommended to do normally. The data is already saved on disk and you can just retrieve it at any time. But you might want to save your source file from time to time, and that's fine. That's much smaller. And so there it is. We did source detection. The next step is to visualize those sources that we found on a cutout of our visit image. So we could just display the full visit image and overplot the sources, but we're taking a moment to make an image cutout instead. There are a variety of ways to make image cutouts. There's a image cutout service that uses the tap service instead of the butler. Or you can use SIA, but it's basically a separate service, and it does server side cutout. So you say, only return to me this piece of the image that I want. And so it saves on bandwidth if you use the image cutout service when you know exactly what the cutout is that you want. In this case, we've already retrieved the full visit image into memory, and now we just want to say, give me a little cutout because I just want to display a smaller region of my image. So it's just a different way to do the cutout. This uses, when you're doing a butler-based cutout, using what we call the factory method that uses the butler to make a little cutout to display, it uses the visit image that you obtained from the butler. It uses the bounding box. It needs to know the origin, so what it thinks of as the pixel 1,1, what that corresponds to. And okay, and we're going to give it the option, the deep option, which makes a copy instead of just passing a reference. Did we actually use that? Oh, we're going to say deep is false. Okay, that's great. All right, so we're going to define our cutout in pixels, a central pixels, and then a width and a height. And it's going to do, it's going to create the bounding box object that corresponds to that X and Y and that width and height. Great. Option to display what a bounding box looks like. It's just special formatted information of the center and the extent. Pretty easy. An alternative there for defining bounding boxes, but this is the part that we really want. We want to make the cutout of the visit image using the bounding box that we made, with these two mandatory things also being passed. And now we're about to display just the cutout from our visit image. So I'm going to switch to side-by-side view with Firefly here. In case you missed that, it's click on the tab and you can drag it to sort of be wherever you want. I like to put the Firefly window over to the right so that I can see everything. The next cell both displays the cutout, and then a mask is typically overplotted by default, but then it obscures the pixels. So we want to set the mask transparency to be 100% transparent at the same time so that we just see the image. Very nice. And here we're about to loop over every source. And so long as the source's X and Y pixel coordinates are within the cutout that we defined, we're going to draw an orange circle at the location of the source. If you didn't have this display buffering, with display buffering, it would, every time you displayed a new dot, it would refresh the entire screen. So the screen would go like this, and it would have a new dot like every time until it had plotted them all on it. But with buffering, it just sort of stays open, and every source gets plotted onto it, then it refreshes. So always use that with display buffering when you're going to be overplotting in Firefly. And there we go. There are the things that we found. And that's all this notebook does. You could do more with this, such as you could go to the source table, which only has signal to noise ratio greater than 5 objects, and you could compare the faint ones that you found with, the ones that were in the source table. You could do things like comparing the photometry that you measured. You can do things like changing the configurations, remeasuring things. Later, we will have other tutorials that do more with deblending and measurement, but for now, this is sort of the simplest one. Did I see that many of the pixels positions are integers in the as AstroPy? Interesting. Yeah. I think that's a no, because the centroids, these are basically, I mean, some are, but most aren't. And I don't know why some might be integers and some not, but sure it has to do with this and what kind of sources they were. So we might find that they are potentially artifacts or single pixel detections, which would be weird. Yeah, if they don't have an extent and they're a single pixel, then you might end up with an integer. But I don't know exactly. I see multiple detection of the same source. Oh, so that might be a case where a source has been deblended and so it's not actually the same source. I think what you must be referring to is probably, for example, here. What has happened in this case is that when we did source detection, the source detection found one object. Then when the deblender ran, the deblender deblended it into two children. Now in our source table, we actually have three things at this location. We have the original, the parent, and then we have the two children. And that is what has happened. That's why it looks like multiple detections. So because rerun source detection and the blending yourself, your source catalog that you get from this particular notebook has parents and both children. And so you get a bit of a duplicate because the parent is technically a duplicate of the children, like especially if it's one object with like a little one next to it. The parent is like the main object, and once it's deblended, one of the children is still kind of the main object, and then the second child object is next to it. So you get duplication. In, for example, the object catalog and the source catalog, those catalogs that are like the user-facing, queryable source and object catalogs, the parents are not in that. So there is not duplicates in those catalogs, but because you've rerun it here, you do get both. So I think that answers the question of multiple detections. And then the how to deal with it, there are parent flags and child flags in the source table. So if you wanted to, this is more for the deblending notebook than really for this one. Yeah, there are, in here you will find flags for like, is it a parent, is it a child? And so you'd be able to go through and say like, only give me children to work with using those flag parameters. Yeah. Any other questions on this source detection, deblending, and measurement? Because we still are doing a second notebook. We're going to do the force photometry one right after this. Alrighty. Let's grab our next tutorial. So go back to the tutorials menu. Again, DP1. Again, at the 100 level how-tos. And our 105 series on image reprocessing. And this time let's open the 105.3 force photometry tutorial. Okay. So in the last notebook that we just did, the first step was to go through and find all the sources. Then we did the blending and then we measured at the locations of the sources we had just found. Force photometry is typically used when you have an RIN deck and you think there's a source there. For example, there's a known variable star that might be subthreshold in your given image, but you know it's there. And so you want to do force photometry. You know it's there, you know it's a point source. You do force photometry to say, get me the measurement, even though this object wouldn't technically be detected because it's too faint in this particular image to be detected. I don't care. I want you to say, give me the flux, assuming that it's there and assuming that it's has the shape of a point source and is a PSF. That's generally what force photometry is used for. So it's often used in the time domain to get flux measurements at a given location, at a given time for objects, for example, when they're faint or as they're fading, or to look for basically subthreshold appearances or subthreshold flux for known time domain objects. But really, it's kind of anytime something is faint or below detection thresholds, and it's a point source, you can use force photometry. There is not exactly a single task in the same way that we use tasks in the last notebook, but a driver task for forced measurements has been created for users so that you don't have to create a pipeline and string some tasks together and sort of do a different type of execution, as is done in some of the other 105 level notebooks. So this is a special case of a sort of a specific use driver task for force photometry that has been made, and we're going to be using it in this tutorial. So it's called forced measurement driver task, and it does force photometry. So for this particular notebook, we just import again the butler, numpy, always butler for data access. And then from this particular measurement driver, we'll get the config and the task to use. As always, we need to instantiate our butler connection. Second section, very similar to getting the visit image in the last notebook that we did, except this time we are going after a deep coad. So we're using a stacked image at the same location and also in the R band. So to find the location, this is the center of the ECDFS field. Define the query again using ARIA and DEC and band, except this time we're asking for deep coad images instead of visit images. So it's a deep stack. We get the exposure. So this is actually returning the pixel data for that deep coad. And then at the same time, we're going to get objects from the object catalog via the butler. Typically for catalog access, and as you will find in the 100 level series on catalog access, we recommend usually that the tap service is used for access to source and object catalogs. But in the cases where you want all of the objects for a given tract and patch, and by that I mean a given like deep coad image corresponds to one patch of the sky map, when you want all of the objects in that given place, like associated with a given deep coad image, and when, especially when you want like just a few columns, but for every single object, the butler works very well as a catalog access mechanism in that case. What you can't do is say, oh, only get me the bright objects in this location from the butler. Butler doesn't work like that. It's going to give you all the rows, it's going to give you all the objects for a given location, but you can select which columns you want. Whereas with the tap service, you can say, oh, just give me all the bright objects, or only the point sources, or only the ones with this color. You can do a lot more query constraints using the tap service on like rows, on the objects that get returned, versus butler access, you're getting everything for a given image. So it kind of depends on your use case, whether you're using butler or tap for catalog access. Most science use cases are tap. Tap is more appropriate. But in this case, we've got a deep coad image and then we want all the objects in that deep coad. So we are using the butler. For catalog access, but remember also that tables are super wide. The object catalog has 1,000 columns. We do not need them all for this notebook. We only need 5. So we're making sure to define which columns that we want to retrieve for all objects using this statement here. All right, so we've got our deep coad. We've got all the objects that are in the tract, which is, so the deep coads are per patch, and a tract in the sky map is made up of multiple patches. We don't need the objects that aren't in our particular deep coad. So that's what the next cell does, is it says, okay, just get me the objects that are in the particular patch that's associated with the deep coad that I just got. So now I just have one deep coad and only the objects that are detected in that deep coad. That's great. You can see that there's about 11,000 objects in our particular patch, in our particular deep coad. And we are not rerunning force photometry for all of them in this tutorial. We're just picking the first 5 from this list and making a table of their object ID, RI, and DEC. Just to make our lives easier, we're just going to do force photometry at 5 locations in the deep coad. And we're going to use these locations somewhat arbitrarily. All right, so now that we're set up, we've got the image, we've got some locations at which to do force photometry. We are ready to set up and configure the force measurement driver and then to run it. This cell is mostly just demonstrating how to set configuration parameters. It's not really changing any of the defaults, I don't think. It's just sort of setting some to show you how to do it. Yeah, so you can pick that you want to return a PSF flux. That is very normal. Yeah, your centroids X and Y will be from coordinates. Yep, that makes sense. Yeah, as it says, these are simply examples of how to set configuration options. They're not recommendations, they're just examples. All right. So we set those configuration parameters, and then this looks very similar from the other notebook where you're passing it the config and defining force measurement driver task as driver. So we've created the task that we're going to run. And now we pass table, exposure, and tell it a few things about the information that we're passing it, the locations that we want, and BSF footprint scaling factor used to create synthetic footprints since detection is skipped from force photometry. Oh, okay. Yeah, since we aren't doing detection, and the step of saying at this location, it's these pixels that are associated with the object, this basically just sets, at every location that you've got, we're using a PSF. I don't know why 3 though. That's actually something to ask the creator of this notebook about. I'll just write it down. Why 3? I don't know. If anyone else from the CSD happens to be here today and knows why PSF footprint scaling was 3 and not 1, that would be good. The notebook does not explain it. We'll get that updated. 1052. Okay. All right, this again has given you some feedback, some output, measuring 5 sources as expected. We only gave it 5 sources. And we have our results, only for 5 because that's all we told it to do. And again, like the other tables, the measurements that it does are a lot. So these tables are very wide and contain a lot of things. That's where this particular notebook ends. It doesn't do anything with the measurements that are made at this particular time, but we could do something just to have some kind of plot. Yeah. So if we just want to make a plot, let's import matplotlib, and then it mentions that your PSF flux is in this column and the aperture fluxes were also created in this other column. So we can just plot the two. I already tried this, so I know there's a typo here that also has to be fixed. It's capital P. Oh, it is not plural. Okay, so in this case, we only made 5 measurements. So the fluxes for the 5 are plotted versus each other. But say you did a lot more, whatever. Mostly I just wanted to show you that this is how you access. You can access the columns. And if you wanted to know what are all the columns that it measured, result.call names gives you all of them. And that's it. This notebook just wanted to show you how to use the measurement task driver to do force photometry at any locations you desired in an image. That leaves us, yeah, that's pretty much it. That's all I wanted to show you for today. But we can do some more questions.